Today we're going to look more at contact forces. I'm going to do two problems and they take a while, so that'll probably be the whole video. So what we've got here are two boxes, and again we're pushing on them. But we're only pushing on the yellow box. We're not pushing on the blue box. The blue box is going to move because it's in contact with the wall, the side of the yellow box. The most important thing is to draw the free body diagrams. So let's draw them right above the boxes. So the 5 kilogram box has mg pulling down and normal pulling up. Normal is the support from the table. And it's getting pushed by a 45 Newton force here. Now there's another force and we'll deal with that in a moment. The blue box has the weight, the mg, and I'm going to use a capital M because it's the bigger box. Some places use M1 and M2, but I'm going to use capital M, and a normal going up. The only reason the blue box moves is because there's a contact force between the two boxes. So C is what moves the big box. But for every force, there's an equal and opposite force. So pushing back on the yellow box is the contact force, which I'm calling C. It's negative for the yellow box, pushing towards the left there, towards the negative axis, because you can think of the blue box as resisting. So now we've got to set up our equations. We're going to set up two boxes, one for the yellow, or two equations, excuse me. One for the yellow and one for the blue. We only care about motion in the x direction right now because it's sliding across the floor. So we bring that down. So MA, 45 newtons is the force that's pushing the box to the right in the positive x direction, and the contact force is resisting. Now the mass of that box is 5, so 5A is 45 minus C. And although we might like to try to go a little farther, we actually can't at this point because we have two equations and two unknowns. And because of that, we're going to need a second equation. And we get that from the blue box. So for the blue box, the sum of the forces in the x direction is MA. Bring that down to the next line. The only force moving the blue box in the x direction is the contact. You say, well, what about the y? You could almost just pretend they don't exist or put your fingers over the normal and the mg. So MA is 10, and there's the contact force. And we can't do anything more with that equation either because there's two variables. But we have two variables and two equations, so we can use systems of equations. I'm just going to rewrite this one down here and rewrite the other one down below it. You might say, why are you leaving that big space? Because I want the C's to line up. So I get 15A is 45. Divide both sides by 15. I'll go over here. A is 3 meters per second squared. That's a pretty good acceleration. We're really accelerating and speeding up those boxes. Now, how can we get the contact force? We can substitute. And I think the easier equation is this one. You can use the first one, but why not make your life easy? So 10 times 3 is the contact force. Contact force is 30 newtons. That 30 newtons is the same. It's 30 newtons in the positive direction for the blue box and 30 newtons but pointing in the negative direction for the yellow box because it's resisting on the yellow box. Okay, now we'll see another example with two old friends probably. So we're pushing on Patrick. Patrick's right next to SpongeBob there. We're going to find the force of contact and all that information. So let's see what we know. We're going to have to draw a free body diagram. We'll draw two of them. So we'll assume Patrick is heavier, mg, and there's the normal force. Just from the diagram, we push with 60 newtons. We're going to have that other force. We'll deal with it in a moment. Now, SpongeBob is also mg, and there's a normal force. The 60 newtons does not go on SpongeBob's free body diagram. We're not directly pushing on SpongeBob. The only thing that's moving him is the force from Patrick's body, the contact force. So the contact force is pushing on SpongeBob, and it's resisting on Patrick. Now we're going to be able to solve the equation. Let's set up Patrick here. Let's set up SpongeBob over here. And it says they're accelerating, in fact. So the sum of the forces, we only care about the x direction for right now, is ma. So ma is the 60 newtons. That's positive. We're pushing towards the positive x direction. The contact force resists. Oh, well, let's see what we know. In this case, we don't know the a, or the m. We know the a is 2. This is 2 right here, meters per second squared. So I get 2m is 60 minus c. Now let's check SpongeBob. The sum of the forces in the x direction is ma. Bring that down. I should have drew the arrow over here too. Bring that down. So ma is equal to the contact force. But this is going to be kind of nice. We know his mass is 10. And we were told the acceleration is 2. That's the acceleration of both of them. If they're in contact, they have to both accelerate at the same rate. One can't accelerate more than the other. So the contact force ends up being 20 newtons. We're able to get that just from the equation here on the right. Here's why that's really nice. We can just substitute that back into that equation. So 2m is 60 minus 20. 2m equals 40. And Patrick's mass is 20 kilograms. And we assumed he was heavier. I think that's a reasonable assumption, at least based on the cartoon. And it all works out. We get our 20 kilograms.